have if a square matrix A is invertible, its inverse is unique. In other words, there's only one inverse. So let's prove this. Suppose we have two inverses. Suppose A prime and A double prime are both inverses of A. We're going to show they have to be the same. Well, then A prime is A prime times I, and this is by the definition of the identity matrix. Then, using the definition of inverse matrix, this has to be equal to A times A double prime. Then we can use the associativity of matrix multiplication to move these parentheses around to give us A prime A times A double prime. But then we can use the definition of inverse matrices again to tell us that A prime times A is the identity matrix, and then we still have this A double prime sticking around. Oh, but then the identity matrix acts as the identity matrix, and so we just get back A double prime. So in other words, A prime and A double prime have to be equal if both are inverses of A. Tombstone. Therefore, instead of writing A prime for the inverse matrix, we take a hint from the way that we have things to the minus first power in real numbers, and we write A to the minus first power for the inverse of the matrix A. Now you might be asking, why do we write A inverse and not 1 over A? So, important, not 1 over A. Well, why not 1 over A? Well, it's because it makes things kind of ambiguous as to whether there's the whole left versus right multiplication thing, and so it's traditional not to write it like that. We always use A to the minus first power when we're writing a matrix inverse. If A is an invertible n by n matrix, then the system AX equals B has the unique solution X equals A inverse B for any B in Rn. And we saw this earlier, specifically in the introductory video for this lesson. Now let's look at an example. Now let's look at an example of how we can apply theorem 3.7. Solve the systems using inverse matrices if A is 1, 2, 3, 7, and A inverse is 7, minus 2, minus 3, 1. And we have these two systems here. So let's start by solving the system on the left. We know from the theorem that our solution is X equals A inverse times 3, 4, which, when we multiply it out, is 21 minus 8, negative 9 plus 4, which is 13 minus 5. And over here, we know, again using theorem 3.7, that X equals A inverse times 2 minus 1, which, when we multiply it out, is 14 plus 2 minus 6 minus 1, which is 16 minus 7. Okay, so that seemed really nice. Why don't we use that method all the time? Well, the niceness here is really kind of an illusion. It's really only nice because I already know what A inverse is, and because I'm dealing with 2 by 2 matrices. In general, this is not usually a very efficient method. In general, row reduction is going to be a lot faster. And moreover, row reduction works even when the coefficient matrix is not square or invertible. However, the method we just used here can be useful if you need to solve a lot of systems with the same coefficient matrix, but with different B.